This is a video lecture for visually impaired students. Chapter number 1, Metal Ligand Bonding in Transition Metal Complexes, from Pradeep's Inorganic Chemistry, Volume 3 by Dr. K. Bhasin. Valence bond theory. Valence bond theory was developed by Linus Pauling. According to valence bond theory, the bonding in metal complexes arises when a filled Ligand orbital containing a pair of electrons overlaps with a vacant hybrid orbital on metal ion to give a coordinate covalent bond. Thus, valence bond theory assumes the bonding between the metal ion and the ligands to be purely covalent. The hybrid orbital that a metal atom uses in accepting the pair of electrons from the ligands are those that point in the direction of the ligands. Valence bond theory successfully explains the structures and magnetic properties of coordination compounds. The salient features of the theory are recapitulated below. The central metal atom or ion in the coordination compounds offer a number of vacant orbitals which is equal to the coordination number of the metal ion for the formation of coordinate bonds with the ligands. The approximate atomic orbitals sp and d of the metal hybridize to give new set of orbitals of equivalent energy called the hybrid orbitals. The hybrid orbitals are directed towards the ligands depending upon the geometry of the coordination complex. The d orbitals involved in the hybridization may be either inner n-1 d orbital or outer n d orbitals. Thus, hybridization in case of octahedral complex may involve d2sp3 or sp3d2 depending upon whether inner or outer d orbitals are used for hybridization. The vacant hybrid orbital of metal ion overlap with the filled orbitals of the ligand and form a coordinate bond, that is L2M bond. Let us take some examples to highlight the feature of valence bond theory to complexes with coordination number 4 and 6. Complex with coordination number 4. Coordination compounds with coordination number 4 are well known. Complexes with coordination number 4 can be either tetrahedral or square planar depending upon whether the hybridization is sp3 or d2 dsp2 respectively. Some of the most commonly found examples are discussed below. Formation of NiCN42 negative ion. The oxidation state of nickel in the complex sign NiCN4 2- is +2. We can represent the electronic configuration of Ni2 positive ion by losing 2 electrons from the outermost 4s orbital. Electronic configuration of nickel is argon 3d8 4s2. Thus the electronic configuration of Ni2 positive ion is argon 3d8. 8 electrons present in the d orbitals of Ni2 positive will occupy in such a way that we shall have 3 of the 3d orbitals occupied by 2 electrons while the remaining 2 3d orbitals are singly occupied as shown in figure 1.1. There are two ways in which the coordination complexes of nickel with coordination number 4 can be formed. If the complex involves sp3 hybridization, it will have tetrahedral structure. On the other hand, if the complex involves the sp2 hybridization, it will have a square planar structure. In case the complex ion acquires tetrahedral structure, the hybridization is sp3. It means that the two unpaired 3d electrons are not affected. As a result, the coordination compound with sp3 hybridization will be paramagnetic. However, the square planar structure, which involves d-sp2 hybridization, requires one of the 3d orbital vacant for hybridization. This is possible only if the two unpaired 3d electrons are paired up. Pairing makes one of the 3d orbitals empty. During this exercise, no unpaired electrons are left and the complex should be diamagnetic. It has been experimentally observed that the complex NiCN42 negative is diamagnetic, which conclusively indicates that the hybridization is dsp2. Secondly, it has no unpaired electrons. Second, formation of NiCl42 negative. The oxidation number of nickel is NiCl42 negative is +2. This is obtained by the loss of two electrons from the 4s orbital of nickel. Experimentally, the complex has been found to be paramagnetic, corresponding to two unpaired electrons. It implies that the 3d orbitals are not disturbed and the complex involves sp3 hybridization. As a result, the structure of the complex is tetrahedral. Third, formation of CuNH342 positive. An inspection at the complex CuNH342 positive reveals that the oxidation state of copper in the complex is +2. The resulting electronic configuration of Cu2 positive is argon 3d 9. According to Hund's rule, the 9d electrons occupy the five 3d orbitals and only one orbital is singly occupied. In order to accommodate four ammonia molecules around Cu2 positive, the metal ion exhibits two possible geometrical arrangements for the complex. If the complex is tetrahedral, it will involve sp3 hybridization and the complex will be paramagnetic. On the other hand, if the complex happens to be square planar, it will involve dsp2 hybridization and the complex will be paramagnetic again. Now, a natural question arises: which of the two structure of CuNH342 positive is true, that is tetrahedral or square planar? Crystal structure determination of the compound has revealed that the complex CuNH342 positive has a square planar structure. It implies that dsp2 hybridization must be involved with one of the 3d orbital made available for hybridization. This can be done by promoting one electron of the 3d orbital to a higher energy vacant for p orbital. Once the electron is promoted into the higher energy orbital, it becomes unstable and can be lost easily. It means that Cu2 positive complex can be easily oxidized to Cu3 positive complex. However, it is not true because Cu3 positive ions are practically unknown. In brief, the above representation of CuNH342 positive ion is inadequate. Although it explains the square planar geometry together with the magnetic moment of the complex, it fails to explain that Cu2 positive can be easily oxidized to Cu3 positive. This anomalous behavior can be easily answered if it is considered that the electrons in the 3d orbital are not perturbed at all and the hybridization involves outer 4d orbitals. This model explains not only the square planar geometry together with magnetic moment but also the stability of Cu2 positive ions which do not undergo any easy oxidation to Cu3 positive by loss of electron. Fourth, formation of NiCO4. NiCO4 is a unique compound in which the oxidation state of nickel is 0. The electronic configuration of nickel is argon 3d84s2. Since the coordination number of nickel in tetracarbonyl nickel is 4, the compound can acquire either of the two structures, that is tetrahedral or the square planar. Since in both the cases 4s orbital are used in hybridization. Therefore, 4s orbital must be made vacant either by promoting 4s electrons to higher energy orbital, or by forcing 4s electrons to occupy the vacant 3d orbital 3d orbital with spin paired. In the first case, where the 3d electrons are promoted to occupy higher energy 4b orbitals, the compound NiCO4 will be paramagnetic as the electrons are not spin paired. On the other hand, when the electrons are forced to occupy the 3d orbitals, the compound NiCO4 will be diamagnetic because the forced 4s electron have no another option but a pair with the two unpaired electrons sitting in the 3d orbitals. Since the compound NiCO4 is experimentally found to be diamagnetic, the nickel atom prefers to involve sp3 hybridization. Let us apply the postulates of valence bond theory to explain the bonding in other coordination complexes with coordination number 6. Examples of complexes with coordination number 6. First, formation of CrNH3 3 positive complex ion. The oxidation state of chromium in CrNH3 3 positive ion is plus 3. The electronic configuration of chromium is argon 3d54s1. Thus, chromium in plus 3 oxidation state is formed by the loss of 1 4s and 2 3d electrons. Two vacant 3d orbitals, 1 4s and 3 4p orbitals of chromium are hybridized to give d2sp3 hybrid orbitals. In other words, chromium 3 positive provides 6 empty orbitals to accommodate 6 pairs of electrons from 6 molecules of ammonia. The resulting complex CrNH3 3 positive involves D2sp3 hybridization and is octahedral. The presence of 3 unpaired electrons in the complex makes it paramagnetic. Formation of CONH3 3 positive. The electronic configuration of cobalt is 3d74s2. The oxidation state of cobalt in the complex is plus 3, which is obtained by the loss of 2 4s and 1 3d electron. Thus, the electronic configuration of cobalt 3 plus is 3d6. In this arrangement, there are 4 unpaired electrons and 1 paired electrons in the 3d orbitals. In order to acquire octahedral geometry, the complex should have D2sp3 hybridization. This can be achieved in the two ways. The two electrons in the 3d orbitals are either paired up with the electrons in the other 3d orbitals, thus leaving the other 3d orbitals empty, or the two 3d electrons can be pushed into the higher energy vacant 4d or 5s orbital. Since pairing of electrons require less energy than promoting to higher energy orbitals, the electrons prefer to pair up. Two vacant 3d orbitals, 1 4s and 3 4p orbitals of cobalt are hybridized to give 6 d2sp3 hybrid orbitals. In other words, CO3 positive provides 6 empty orbitals to accommodate 6 pairs of electrons from 6 molecules of ammonia. Since there are no unpaired electron in the 3d orbital in the complex sign CONH3 3 positive, it should be diamagnetic. Experimentally, it has been found that the complex is diamagnetic. Formation of COF6 negative. As already discussed, the electronic configuration of cobalt is 3d74s2. The oxidation state of cobalt in COF6 negative is plus 3, which is easily achieved by losing 2 electrons from 4s and 1 electron from 3d orbital. The electronic configuration of CO3 positive is 3d6. The complex ion COF6 negative has been found to be paramagnetic, which suggests the presence of unpaired electrons. However, this behavior is found to be paramagnetic, which suggests that the presence of unpaired electrons, altogether different from what we observed in case of CONH3 3 positive. It amounts to saying that the orbital geometry in case of COF6 negative cannot be attributed to D2sp3 as found in case of CONH3 2 positive.
In an effort to explain this distinct behavior, Lewis polling suggested that the complex CuF63 negative is ionic and the metal Ligand bonds are ionic. This appeared justified at the time in the view of the highly electronegative character of F negative fluoride ion. However, it was soon discovered that other complexes like COH2O3 F3, FeH2O63 positive, and NiH2O63 positive were found to be paramagnetic since the bonding between the metal and the water and these compounds cannot be ionic. It suggests that the Pauling formation of ionic bond between metal and the Ligand is not correct. An alternative explanator was proposed by Huggins in 1937 to explain the anomalous magnetic behavior of COF63 negative by suggesting that the metal can use outer d orbitals for hybridization in place of inner d orbitals. This formulation kept the inner d orbital undisturbed and the use the outer 4d orbitals for hybridization. Thus, 6 sp3d2 hybrid orbitals are formed from 1 4s and 3 4p and 2 4d orbitals. 6 pair of electrons are donated to the 6 vacant hybrid orbitals of the metal forming COF bonds. It is clear from the above discussion that the central metal atom has the ability to use either inner n-1d orbitals or outer nd orbitals for hybridization depending upon the Ligand and the magnetic properties of the complex. In case the coordination complex uses the inner n-1d orbitals for hybridization D2sp3, it is called the inner orbital complex. On the other hand, if the coordination complex uses the outer ND orbital for hybridization sp3d2, it is called the outer orbital complex. In case of inner orbital complex, the metal electrons prefers to pair up. As a result, the complex will be either completely paired or will have lesser number of unpaired electrons. This type of complex formed is called low spin complex. On the other hand, in case of outer orbital complex, the electrons of the metal prefer to remain unpaired. As a result, the complex will have more number of unpaired electrons. This type of complex formed is called high spin complex. Formation of MnCn6 for negative. The electronic configuration of manganese 25 is 3d5 4 s2. The oxidation state in the complex is +2, which is obtained by the loss of 4s electrons. Therefore, the electronic configuration of Mn2 plus is 3d5. The magnetic moment of Mn6 for negative has experimentally found to correspond to the presence of a single electron. This can be easily accounted for. The four 3d electrons are paired up, leaving behind one unpaired electron along with the two unoccupied 3d orbitals. Now, six vacant orbitals intermix together to give sp3d2 hybrid orbitals. These hybrid orbitals can have six pairs of electrons from the six cyanide ions to give an octahedral geometry. The complex MnCn6 negative short reduce paramagnetic behavior corresponding to the presence of only one unpaired electron. What would you like to call this complex? An inner orbital and outer orbital complex. This is an example of low spin complex because of reduced magnetic moment value. Fifth, formation of FeH2O6 3 positive ion. The oxidation state of iron in the complex is +3. Electronic configuration of iron in zero oxidation state is 3d6 for S2. Electronic configuration of Fe3 plus is 3d5. The complex FeH2O6 3 positive has been found to be paramagnetic and the magnetic moment corresponds to the presence of 5 unpaired electrons. It clearly indicates that the 3d electrons are not disturbed at all. In addition, the outer 4d orbitals are used up for hybridization. It means 1 4s, 3 4p, and 2 4d orbitals are hybridized to afford 6 sp3d2 hybrid orbitals which are occupied by six pair of electrons, one from each water molecule. Six coordinate bonds are formed by donation of six electron pairs from six H2O molecules. Thus, FeH2O6 3 positive is an octahedral molecule with paramagnetic behavior. It is important to remember that the geometry and hybridization go hand in hand. If you know the geometry of a complex, you can easily know which hybrid orbitals the metal atom ion uses. The relationship between the geometry of the complex and the hybrid orbital used by the metal ion is nicely summarized in table 1.1. Limitations of valence bond theory. The valence bond theory extended by Linus Pauling to the coordination compounds in terms of orbital hybridization was successful in interpreting the geometrical shapes of most of the complexes. However, the theory failed to account for several properties associated with the complexes. For example, it fails to explain the color and spectra of the complexes. It fails to explain the differences between the measured and calculated magnetic moments, although this theory successfully help in predicting the number of unpaired electrons in the complex. It also fails to explain why the magnetic moment values varies with temperature. The theory fails to explain to the relative stabilities of complexes. It fails to explain why some complexes are labile while others are inert. Labile complexes are those in which one of the ligand can be easily displaced by another ligand. On the other hand, inert complexes are those in which the displacement of ligand is slow. It does not predict whether the four coordinate complex species will be square planar or tetrahedral. For example, the decision about the geometry of nickel 2 species depend upon the value of magnetic moments. It considers nickel acetate 2 to be the tetrahedral, whereas in fact it has octahedral geometry. The theory fails to explain why some metal complexes in a particular oxidation state are low spin, that is inner orbital complex, while some other complexes of the same metal ion in the same oxidation state are high spin, that is outer orbital complexes. For example, CONH363 positive and COF63 negative, in which cobalt is in +3 oxidation state, the former is low spin while the latter is high spin. Crystal field theory. Valence bond theory helps to understand the bonding in coordination compound. However, the theory suffers because it neither accounts for the color of the coordination compounds nor explains why some complexes are high spin whereas others are low spin. Crystal field theory, on the other hand, explains successfully the color of the complexes as well as their magnetic properties. This theory was developed by the physicists named H. Beth and V. Black to account for the color and magnetic properties of hydrated salt of transition metals. Originally, crystal field theory was applied to transition metal ions in ionic crystals. That is why this theory is called crystal field theory. Chemists began to apply the crystal field theory to transition metal complexes in 1950s, and since that time inorganic chemistry has become an excited field of research. Crystal field theory considers the central metal ion and the surrounding ligands as point charges. Point charges are electric charges that exist at a single point. It is important to note that the point charges has neither an area nor a volume. According to crystal field theory, it is the electrostatic attraction between the positively charged on the central metal ion and the negative charge on the ligand that holds the ligand to the metal ion. In brief, crystal field theory assumes the bond between the metal ion and the ligands as purely electrostatic. In case the ligand happens to be negatively charged ions such as Cn negative, Br negative, I negative, etc., the interaction between the metal and the ligand is referred to as ion-ion interaction. In case the ligands happen to be the neutral molecule, it can be considered to have a dipole moment as in ammonia NH3. The nitrogen in the NH3 acquires a negative charge, partial negative, and the hydrogen acquire a positive charge. In such cases, the interaction of the d metal ion with the ligand is referred to as ion dipole interactions. The d orbitals and crystal field theory. Since d orbitals are frequently used in coordination compounds, it is more important to study their shape and distribution in space. In order to understand crystal field theory, it is necessary to look again at the spatial orientation of all the 5 d orbitals relative to the position of ligands in the metal complex. There are 5 d orbitals and are designated as dxy, dyz, dzx, dx square minus y square, and dz square. The boundary surface of these orbitals as one subset of three orbitals dxy, dyz, dzx are similar in shape and each consists of four lobes of high electron density lying between the xy, yz, and zx plane respectively. The lobes of those orbital lies in between the principal axes. There is another subset of two orbitals dx square minus y square and dz square. The orbital dx square minus y square consists of four lobes that lie along the x and y axis. The orbital dz square consists of two lobes that lie along the z axis and donut called a torus in the xy plane. It is important to point out that all the dz square and dx square minus y square orbitals do not look alike in shape, yet they are equivalent as far as their interaction with the metal ions are concerned. The unique shape of dz square orbital can be regarded as a linear combination of two orbitals, that is dz square minus x square and dz square minus y square, each of which is equivalent to dx square minus y square. Since both the orbitals dz square minus x square and dz square minus y square have high electron density along the z-axis and dz square orbitals has a large amount of electron density concentrated along the z-axis, since one of the component wave function is maximized along the x-axis dz square minus x square and other along the y-axis dz square minus y square, the resultant dz square has a torus of electron density in xy plane. However, both the orbitals dz square minus y square and dz square minus y square do not have independent existence. Assumption of crystal field theory (CFT). Crystal field theory is now more widely used than the valence bond theory. It considered the attraction between the central metal ion and the ligand in the complex as purely electrostatic. The basic assumptions of the CFT are the following. First, the transition metal ion is surrounded by a number of ligands with lone pair of electrons. Second, the ligands are treated as point charges. Point charges are the electric charges that exist as a single point. It is important to remark that point charge has neither an area nor a volume. Third, the ligand may be neutral or negatively charged species. In case the ligands are neutral, it is negative and of the dipole that is oriented towards the metal ion in the metal ion that accounts for the electrostatic interaction. In case of negatively charged ligands, the interaction between the central metal ion and the ligand is purely, that is 100% ionic. Fourth, all the 5d orbital of the isolated gaseous metal atom have the same energy. These 5d orbitals of the gaseous atom possessing the same energy are called degenerate orbitals. If a spherically symmetric field of negative charge is placed around the metal ion, all the 5d orbitals of the metal will be raised in energy as repulsion between the negative field and the negatively charged electrons of the orbitals. In brief, the energy of the orbital is raised because of the repulsion between the field and the electrons on the metal. However, the energy of the 5d orbitals will still remain degenerate. If the electric field results from the influence of real ligands, either from negatively charged anionic ligands or negative and of the dipolar ligands such as NH3. The electric field is not spherically symmetrical because of finite number of ligands involved. In such a case, the d orbital are not affected equally by the electric field of ligands. We have also noted that the d orbitals have different orientation in space, and therefore these orbitals will experience different interaction from the ligands. The orbital lying in the direction of the ligand will experience greater repulsive interactions, and consequently their energies will be traced. On the other hand, the metal orbital lying away from the ligand will experience lesser repulsive interaction. As a result, their energies will be raised to a smaller extent. In summary, the energies of the 5d orbital of the metal are split up due to the electric field generated by the ligand surrounding the metal. The splitting of energy of the 5 degenerate d orbitals of the metal ion into two different set of orbitals to different energies in presence of electrical field of ligand is called crystal field splitting. Fifth, the number of ligands surrounding the metal affects the energies of 5d orbitals. It means that the crystal field splitting will be different with different coordination numbers. The properties of the coordination, such as magnetic properties and color of the compound, can be easily explained in terms of splitting d orbital in different crystal fields. Crystal field splitting in octahedral complexes. In octahedral complexes, the metal ion is at the center of octahedron, whereas the surrounding ligands are at the sixth corner of the octahedron. Let us consider first a metal ion without any ligand surrounding it. In this case, all the 5d orbital possess the same energy and are called degenerate orbitals. This is represented by 5 lines at the same level on the left. Let us now place this metal ion in a spherically symmetrical electric field consisting of 6 negative charge electron present in the metal d orbital will interact repulsively with the electric field of the 6 negative charges. This repulsion between the like charges raise the energy of the d orbitals equally by amount. Let us now consider the electric field generated by 6 charges placed at the varieties of an octahedron on the x, y, and z axis. It is important to recall that the total charge around the metal ion is the same, but its distribution is different, and hence the surrounding charge is not spherically symmetrical. Shows that dz square and dx square minus y square orbitals points directly towards the 6-point charges representing the ligands. These two orbitals interact directly and strongly with the ligand charges. As a result of strong repulsive interaction, the energies are raised. The other three orbitals, that is dxy, dyz, and dzx, are not affected as much to dz square and dx square minus y square. As a result, the energies of dxy, dyz, and dzx are lower. It is important to note that the energies of dz square and dx square minus y square orbitals are precisely equal. It means that these two orbitals are degenerate. Similarly, the three orbital dxy, dyz, and dzx are also degenerate. dxy, dyz, dzx orbitals are in equivalent environments in octahedral geometry. It may appear that as dx square minus y square orbital is being repelled more and dz square is being repelled less, it is important to recall that dz square orbital is a linear combination of dz square minus y square and dx square dz square minus y square, and has also electron density in xy plane. As a result, both the dx square minus y square and dz square orbitals are equally affected and are degenerate. The pattern of one doubly degenerate and one triply degenerate orbital is characteristics of all the octahedral complexes. The set of three degenerate orbital is named as T2G. The origin of these names come from the branch of mathematics called group theory. The other set of two degenerate orbital is named as EZ, and the origin of this name occur from the group theory. We have noted so far that in octahedral complexes, the 5d orbital are split up into two sets. One set consisting of three orbitals of lower energy T2G orbitals and other set consisting of two orbitals of higher energy EZ orbitals. The energy difference between two set of d orbitals is called crystal field splitting energy and is abbreviated as CFSE. It is symbolically designated as del naught. The subscript 0 indicate that the complex is octahedral. The actual value of del naught depends upon particular compound and varies with the metal ion, the ligand, and the charge on the complex. Some of these factors will be discussed later. Sometimes another parameters dq is used instead of del naught. These two parameters are related as del naught is equal to 10 dq. Let us consider the approach of Ligand as a two-step process. In the first step, the Ligand approach the metal ions and produce a hypothetical spherically symmetrical field which repel all the orbitals to the same extent. In the second step, the Ligand approach the metal ion and split the orbital degeneracy due to the repulsion to different extents. It is important to note that the crystal field occur in such a way that the average energy of the d orbital remains the same. In other words, the barycenter or center of gravity of the orbitals remain constant during the second step. It means that the decrease in the energy of the set of orbitals that lie at the lower energy level must be balanced by the corresponding increase in other set of the orbitals. Therefore, if the T2G sets drop by 2 units, a balance is achieved if the EG sets rises by 3 units. If the difference between T2G and EG level is defined as del naught, then it is clear that the energy of T2G level changes by minus 0.6 del naught, while the energy of EG set changes by plus 0.4 del naught. In terms of 10 dq in octahedral case, the T2G level is stabilized by 6 dq, while the EZ level is destabilized by 4 dq.
Tetrahedral complexes. Two of the most common geometries of four coordinate complexes are tetrahedral and square planar arrangements. A tetrahedral arrangements of four ligands surrounding a metal ion can be imagined by placing four ligands on the alternate corners of a cube or by placing four ligands on the opposite corners of a cube. A tetrahedral complex can also be imagined by removing four of the eight ligands from opposite corners of cube. The three coordinate axes are defined as those passing through the centers of the cube and the center of each cube face. In this arrangement, the ligands do not directly approach any of the metal d orbitals. However, the ligands come closer to the dxy, dyz, dzx orbitals that are directed towards the edges of the cube compared to the dx square minus y square and dz square orbitals that are directed to the centers of the faces of cube. As a result, the energies of three orbitals, namely dxy, dyz, dzx labeled T2, will be raised, whereas the energy of two orbitals, that is dx square minus y square and dz square labeled as E, will be lowered. Thus, the T2 orbitals are destabilized whereas the E orbitals are stabilized. Further, since the center of gravity rule holds, the T2 orbital are raised 4 dq and E levels are lowered by 6 dq from the barycenter. The magnitude of crystal field splitting delta is the difference in the energy between the doubly degenerate E and the triply degenerate T2 level. The subscript T indicates a tetrahedral complex. It is also measured in terms of dq and is related to del T. Del T is equal to 10 dq. In a tetrahedral complex, as mentioned earlier, ligands do not approach any of the metal orbitals directly. In addition, only 4 ligands split the d orbitals. 4 ligands instead of 6 would result in 33% decrease in the field. The splitting of d orbitals in tetrahedral complexes is is much smaller than splitting in case of octahedral complexes. It has been experimentally found that the crystal field splitting in octahedral field is nearly more than twice as strong for a tetrahedral field for the same metal and the same ligands. It has been found for a point charge model del T is equal to 4 by 9 del naught, that is 10 dq tetrahedral is equal to 4 by 9 into 10 dq tetrahedral. Since the crystal field splitting in tetrahedral field is quite small, it means that the pairing of electron is not energetically favored. It amounts to saying that pairing energy P is virtually always greater than the splitting between E and T2 energy levels. As a result, virtually all the tetrahedral complexes are high spin complexes. Crystal field splitting in tetragonal and square planar complexes. If two translucent is an octahedral complex are moved either towards or away from the metal ion, the resulting complex is called tetragonally distorted. If the two translucent are brought closer to the metal ion, the octahedron tends to flatten. This is called the flattening of the octahedron, in which the two trans ml bonds are shortened while the other 4 ml bonds become longer. If the two mutually trans ligands are completely removed, it is result in the formation of square planar complex. Since the octahedron is symmetrical, it does not matter which two mutually trans ligands are removed, but the axis from which these ligands are removed is conventionally defined as the z-axis. A partial removal of the ligand along the z-axis gives a distorted octahedron. As the ligands on the z-axis are moved away, there is an increase in the metal ligand bond length along the z-axis. The increase in the length of metal, there is an increase in the metal ligand bond along the z-axis. The increase in the length of metal ligand bond decrease in the repulsion between the ligand and the metal electron present in dz square orbitals. As a result, the energy of d orbital is decreased relative to that in octahedral field. On the other hand, if the metal ligand bond along the x and y axis are shortened, the d orbitals in the xy plane, that is dx square minus y square, feels greater repulsion from the ligand and therefore its energy increased. On similar lines, the dxz and the dyz orbitals are lowered in energy, whereas the energy of dxy orbital is raised. In a square planar complex, further increase in the energy of dx square and minus y square and dxy occurs with a simultaneous decrease in the energy of dz square and dxz and dxy orbitals. It has been found that the energy of dz square orbitals falls below dxy orbital in case of square planar complexes. Factors affecting the crystal field parameters. There are a number of factors that affect the extent of splitting of d orbitals by the ligands. These are discussed below. First, nature of ligand. The crystal field splitting depends primarily on the nature of ligand surrounding the metal ion. The greater the ease with which the ligand can approach the metal ion, the greater will be crystal field splitting. The ligand which cause smaller crystal field splitting are called weak filled ligands, and the ligands which cause larger crystal field splitting are called strong fields. Ligands can be arranged in a series called spectrochemical series according to their increasing magnitude of crystal field splitting. Those on the left of NH3 are called weak field ligands, and those on the right side of NH3 are called strong field ligand. The order of spectrochemical series remain practically same irrespective of the transition metal ions. The effect of crystal field splitting on the ligand attached to the chromium and cobalt are given below. Second, oxidation state of metal ion. The magnitude of the crystal field splitting depends upon the oxidation state of the central metal ion. Trivalent metal ions causes larger crystal field splitting than the divalent metal ions. For example, the crystal field splitting in trivalent cobalt complex CuH2O6 3 positive is 18600 centimeter inverse, whereas in corresponding divalent cobalt complex CuS2O62 positive is the CFSE is only 9400 centimeter inverse. This increase in crystal field splitting is due to increase in the charge on the metal ion that tends to pull the negatively charged ligands more effectively towards itself. An, an inspection reveals that the trivalent metal ions play greater crystal field splitting than the divalent metal ions. Third, types of d orbitals. The magnitude of crystal field splitting within the same transition series as shown do not vary greatly. However, appreciable changes 30 to 50% in crystal field splitting occur on moving from 3D first transition state to 4D second transition series. An almost similar increase in the crystal field splitting is observed on moving from 4D second transition series to 5D third transition series. Fourth, geometry of the complex. The crystal field splitting energy in case of tetrahedral complex is less than that for an octahedral complex. This is because there are only 4 ligands in tetrahedral field as compared to 6 ligands in case of octahedral field. In addition, there is a ligand along each axis on the octahedral field, whereas no ligand lies directly along any axis in the tetrahedral field. The splitting in an octahedral field has been found somewhat more than twice as strong as for a tetrahedral field for the same metal and the same ligands. That is del T is equal to 4 by 9 del naught. The splitting energy for tetrahedral complex is small as compared to the pairing energy P. This explains as to why most of tetrahedral complexes are high spin complexes. Thank you.